Hello, everyone. We're going to be starting in a few minutes. We're just going to wait for a few more people to arrive. Also, we should announce that the talk will be recorded, if that is okay with everyone. Um, and yeah, if there's any objections to that, you can message us. But yeah, just to let you know. Right. Um, Should we get started? Yeah. Okay. Hello, everyone, and welcome to today's climate talk. I hope that you can all hear me okay. Um, our session is titled The State of the World Climate 2025. Has the Earth reached its buffering capacity on CO2 and heat absorption? And to explore this topic, we are very lucky to have Dr. Stefan Sommer here with us today. So before I hand it over, let me briefly introduce him. So Dr. Sommer is a science communicator, a film producer, an author, and public speaker. Um, he's the founding board member and speaker for the Northern Arizona Climate Change Alliance. Um, he's also a founding board member and speaker for NAU's Sustainable Ambassadors Program. And since his retirement, he's been an affiliate in NAU's Department of Biological Sciences and the Centre for Adaptable Western Landscapes. He has expertise in community ecology, sustainability, climate change, and education outreach. Apart from that, he also writes for the Arizona Daily Sun as author and editor of the column Spotlight on Climate Change. And he has served as executive producer of four award-winning PBS documentaries on biodiversity and habitat conservation. So I'm very pleased to have Dr. Stefan Sommer here with us today. Um, and yeah, I'll hand it over, but I'll just briefly like to mention that we ask everyone to keep their microphones muted during the presentation. And then at the end, you can write any questions in the chat. Thank you. Over to you, Stefan.
Thank you very much, Frida. So welcome, everybody. And during the presentation, if I say anything that is unintelligible or for whatever reason you have a question, please put your questions into the chat and then Frida will forward them to me as we go. And that way I'll be able to get through the amount of material that I put together for today. Let me go ahead and share my slides. Can everybody see that okay? Very good. Okay. So again, my name is Stefan Sommer. I've been working with the Northern Arizona Climate Change Alliance since it was founded by Rolf vom Dorp back in 2016, 17. And we've been quite active in doing outreach about climate change. So this is part of a speaker series that NASCA does on a regular basis called Climate Talks for Everyone. And it goes out globally through Fridays for Future International, as well as locally and regionally through Northern Arizona Climate Change Alliance. And so we'll talk today about the state of the world climate. And I imagine, since you are here, you probably already have an interest in climate, and you probably know basically what is going on with climate change. So we'll focus today initially on what's new in climate change science, and then uh, we'll talk about some basics to get us all on the same page. Recent temperature rise, which has taken another leap. What are the Earth's buffering systems? How has the Earth been buffering the effects of our input of fossil fuel related CO2 and other sources? And then what's going on with emissions? Are we reining them in? And then I want to focus, usually when I present on climate change, I cover the basics and then I shift into what are all the details of what the effects of climate change are. I believe that y'all are probably familiar with what's going on with climate change. And so what I would like to do this time is talk a little bit more about what people are doing and what we can do to help rein in our emissions and focus that way. I certainly the effects of climate change are intensifying. We we know that for the United States, for example, many insurance companies are now going out of business. Particularly, they're closing shop in Southern California and Florida because of wildfires in California and hurricanes in Florida. And we know that the real estate industry says that housing values in the United States will drop by $1.4 trillion because of climate change. So we know that there are these direct climate impacts and then effects on our economy, but we'll delve more into what people are doing and what we as individuals can get involved in. Okay, so when we're understanding climate, it's really important to understand we can't understand today without knowing the past. And this is a prime example. So here we see the temperature, average global temperature since 1880, in this case up through 2016. And to understand 2016, we can't really do it without seeing what's happened in the past and how different we are from what was in the past. And so that's really a theme throughout all climate change research, is comparing the present to the past and how are we different? And then from there, what might be the consequences? And then also, why are we different than the past? And I think we know, by and large, we know the answer to that. And so we won't focus a whole lot on that, but a little bit. So one of those ways that we compare ourselves to the past is through ice cores in Antarctica. Um, and so we can take these ice cores. Here's a picture of an ice core, and you can kind of see there are little striations in there. Each layer of ice is a year of snowfall on Antarctica. The next year compresses that year and so forth. And so each new layer up is more recent. And so we can go through those layers and see how the Earth's temperature has varied across that time period and how the atmospheric composition has changed because of looking at what's inside of the little ice bubbles in each of the different layers. The way we can get a temperature record out of this is by looking at the ratio of normal weight water to heavy water being H2O molecule that includes a heavy hydrogen, it's called deuterium, or a heavy oxygen. And that just means that those are isotopes of those elements that have extra neutrons and are slightly heavier. So when water evaporates, the heavy water molecules take a little bit more heat energy to evaporate, to turn from liquid into a gas. And so when the temperature of the ocean's surface is warmer, relatively more of the heavy water evaporates and then forms snow, which falls on Antarctica. And so the sea surface temperature, if it's higher, it releases more heavy water. If it's colder, less. And so that ratio of heavy water to normal water in these different layers gives us an idea of the relative temperature from year to year. Does that all make sense? The good thing about this is not only can we get a temperature and an atmospheric composition record, but we can also go back a long way. So this, for instance, is the Lake Vostok ice core system, and it's been cored 3,623 meters, which covers the last 420,000 years of accumulation of snow layers and ice in Antarctica. Now I'm going to show you some of the record of both the atmospheric composition over that time and the temperature. And it won't be the whole time. I'm going to show you the last 160,000 years. So here it is. You may have seen this before. And basically we've got, from those bubbles in the ice, we've got the carbon dioxide concentration in parts per million here. And we've got the relative temperature here. Again, from that heavy water relative to normal water ratio. So a couple different things. This is present here at year 0, and it goes back 160,000 years. So one thing is that the highest across that time has been, plus 280 parts per million of CO2 in the atmosphere, plus or minus a little bit. And that's what we know the pre-industrial concentration of CO2 in our atmosphere has been. So we are kind of at the upper end of this record. And that is the background from which we're measuring current anthropogenic CO2 change in the atmosphere. The other thing is here, so in the past, we've also had rises in CO2 in the atmosphere. For instance, about 130 to 140,000 years ago here. And so we had a rapid rise in CO2 and rapid rise in temperature. Then we had slow decline over time in CO2 concentration and a slow decline in temperature. And this is one of the reasons, one of many reasons, that we understand that CO2 strongly determines the temperature of our atmosphere and the Earth's surface. One thing here, though, why did CO2 rise at that time? Well, that was the end of a ice age, a glacial period. And I'm not enough of a geologist to tell you this for certain, but I believe that during an ice age, a lot of biological material accumulates and freezes as temperatures vary, and as has done for us. So we've got a large amount of permafrost stored in the north that now, as temperatures are rising, is beginning to release. In some parts, if it decays under aerobic conditions, it releases CO2. If it decays under anaerobic conditions, then it releases methane. In any case, so I believe that was the primary cause of this rise in CO2 and the warming that was associated with it. We came out of the most recent ice age around 14,000 years ago. So again, I think this rise in CO2 is related to that coming out of the last ice age. But now we're doing a whole new thing above and beyond the normal CO2 happening after an ice age. And that's shown here. So if that scale was over 160,000 years, this is a much shorter time scale, just 2,000 years. And you can see for the last 2,000 years, the temperature of the Earth has been holding pretty steady. And only in the last 150 years or so has temperature just been skyrocketing. And it has been changing faster than anything in past geological records of the Earth's temperature. So this is the basics of climate science. And I think most of us probably understand this part. What has been happening since 2023 is a whole new thing. So, well, actually, so this This is the record from 1850 up through, this is 2023. And this is the Earth's global average temperature. And you can see it's been rising steadily. We did hit 1.45 degrees centigrade temporarily in 2023. But at this moment, scientists consider that we have raised, with our added greenhouse gases, we've raised the Earth's average temperature by 1.2 centigrade degrees. And that's because we use a 10-year running average. And so it's really got to be high for a long time before we'll acknowledge that. And in any case, we have touched upon 1.5 degrees centigrade warming, but really what we've done so far, the record indicates, is we've raised the Earth's temperature 1.2 degrees. And that might not seem like a whole lot, but if you consider all of the thermal energy involved in raising the temperature of the entire volume of the atmosphere and the entire surface of the Earth by 1.2 degrees, that is a huge amount of heat energy. Okay, so what this here is showing is that since about 2010, the slope of that increase in temperature has gone up. It was about 0.18 degrees centigrade per decade, and since 2010, that is 2012, 14 maybe, it's been going up at a faster rate of 0.26 degrees centigrade per decade. Why would there be that change? Is a big question. This is a very recent analysis by James Hansen, the name you may recognize. He was one of the earliest scientists to testify to Congress, the United States Congress, about climate change. And this is from a paper he just published. And it shows the same thing that I just showed you in the other graph. But basically, the best linear fit, 2010 to present, is a much steeper curve than the 1970 to 2010 curve, which is this green dotted line. Again, the question is why? So if you look at the rise in emissions, they've actually been fairly steady. So I do not think that the rise in emissions explains this sudden increase in the speed of global warming. And so there are potential other explanations, and one of those is that perhaps the Earth has reached its limits in terms of its capacity to buffer the temperature increase and the CO2 increase. And we'll talk about those buffering systems in a moment. So here is our emissions as of yesterday. We had raised the Earth's atmospheric concentration of CO2 from 280 parts per million, the pre-industrial level, to 428 parts per million. Fortunately, that particular website has not been shut down by our new administration yet. They've threatened to. But if you look here at 2010, when we saw the shift in the rate of increase in temperature, there wasn't really a shift in emissions. That rise has continued to rise, but it's been rising fairly steadily. So again, why are we seeing this sudden leap in temperature? Here also, this is from the IPCC report, the sixth assessment report in 2023. And here they break it down in much more detail as to all the different greenhouse gases, not just CO2, but methane and nitrous oxide, and fluorinated hydrocarbons. So again, there was not a massive leap in 2010 that would directly explain the increased rate of warming. So what is it? Well, so the Earth has a couple of different buffering systems. It has many different buffering systems, and we're going to focus on two of them. So for one thing, a lot of the CO2 that we have emitted into the atmosphere actually gets absorbed by processes on the land surface and in the oceans. And so we'll talk about those. And so that we can buffer the amount of CO2 increase with those particular systems. And then also the ocean has been absorbing most of the excess heat that has been trapped by greenhouse gases. So up until this point, 90% of that excess greenhouse gas caused heat has been stored in the oceans and is not remaining in our atmosphere. And thank goodness. I mean, if there wasn't that storage capacity in the oceans, our atmospheric temperatures would have been rising much more rapidly. So these buffering systems are things we don't necessarily think about all the time, but they're very, very important to the overall effects of climate change because they buffer a lot of it. One way to look at this is above the curve is all the CO2 emissions, the CO2 sources, if you want to call them that. So fossil fuel burning is the bulk of it, but also land use changes is another, and cement production is another, not specifically listed here. But the primary ones are fossil fuels and land use changes. And land use changes are things like plowing down a habitat or burning a habitat and causing all the carbon stored in that habitat to decompose or burn and enter the atmosphere as CO2. When we till soil, there's a huge amount of carbon stored in soils. We mix in oxygen by tilling it, and we greatly speed up the decomposition of that carbon-rich material that's in the soil, and that also releases CO2. So of all that CO2 emitted, these are the sinks. 22% of that added CO2 is absorbed in the oceans. And some of it is that CO2 is directly soluble in water. We'll talk about that in a moment. But also there's some photosynthesis. Phytoplankton and other organisms in the ocean can take up CO2 as a raw material for photosynthesis. And the same thing happens on land. So 31% of that added CO2 gets absorbed into terrestrial ecosystems, largely through the process of photosynthesis. And then some of that product of photosynthesis is stored in soils as well. So it's really only the remaining 47% of that emitted CO2 that remains in the atmosphere, and that is the cause of the climate warming and climate change that we have seen, if that makes sense. So again, thank goodness for these buffering capacities, but let's look at them in a little bit more detail. Okay, so the oceans absorb 30 million tons of CO2 every day. A portion of that is through photosynthesis, phytoplankton take up CO2 and so forth. But a lot of it is just because CO2 is directly soluble in water. The problem is that when you dissolve CO2 in water, it combines with carbonate ion to form bicarbonate ions, and those cause the water to turn acidic. So we have been acidifying the oceans by dissolving all this excess CO2 in it. And that acidity impedes not only calcification, so all shelled organisms, as shown in this little image here, have a more difficult time producing those shells when the water is acidic, but also it impedes phytoplankton productivity. And phytoplankton are the source of about 40% of the oxygen in our atmosphere. And what happens is, out in the open ocean, iron is one of the most limiting nutrients. So phytoplankton and other organisms in the upper surface of the open ocean have mechanisms for taking on iron, the scarce iron that is available, and they use a certain kind of molecule called siderophores. And those siderophores have an affinity for iron, and then they're on the outside of the cell membrane, and then the cell membrane has molecules that have a higher affinity, and that transports the iron into the cell. What happens under acidic conditions, though, is that those siderophores have a higher affinity for that iron. And though they then still collect iron, they no longer release it to the cell. And so acidifying the oceans exacerbates the whole lack of iron and reduces phytoplankton productivity. And we won't get into the numbers of that per se, but in any case, it has a variety of negative effects on the ocean. So we're very thankful that that's where a lot of the CO2 goes instead of staying in our atmosphere from a climate change perspective. But we're not helpful. This is not helpful at all in terms of ocean productivity and ocean health because it acidifies the water. For land ecosystems, there's that sink, and most land ecosystems have plants which have major amounts of photosynthesis. Overall, globally, the many different terrestrial ecosystems can store 785 million tons of carbon every year. They take it up because, again, CO2 is a raw material for photosynthesis. And places like the Amazon rainforest then are major stores for carbon. And that's a good thing. Overall, the Amazon rainforest holds about 123 billion tons of carbon. And that's all the biomass that's there. That's not necessarily with the uptake every year. That's simply the standing biomass. And what we've been doing to the Amazon, unfortunately, is clearing forests. And so we've been burning and clearing forests, and that turns a lot of that carbon into CO2 released to the atmosphere. So also, because the climate conditions are changing to becoming slightly drier and warmer, they're more conducive to the growth of savanna type of vegetation. And so the plants that are adapted to live in tropical rainforests are becoming less productive because the conditions are getting less ideal for them. So between those two things, the burning and clearing and the lesser productivity of the remaining plants, the Amazon rainforest is no longer a carbon sink. Starting in about 2018, it became a carbon source. So it is now contributing CO2 to the atmosphere where it used to remove CO2. And this is happening all around the world. Virtually every ecosystem has been hit by climate change. So it's pushing plants from their closely adapted climate conditions, the climate conditions they are closely adapted to other conditions, and their productivity is going down. So most ecosystems on Earth are still carbon sinks, but the strength of that carbon uptake is probably reducing as their productivity declines. Here in northern Arizona, for instance, this is an area, this is Coconino County, Flagstaff is about here somewhere, and we've seen greater than 80% reduction in the productivity of our rangeland plants. This is data from 2018. So we had already seen that at that point. So again, terrestrial ecosystems around the globe are experiencing lower productivity, and as a result, they're absorbing less of that CO2 that we're putting into the atmosphere. And this is not a good thing. So the buffering capacity in the oceans and the buffering capacity on land is decreasing. We know that. Another huge buffering thing is that the oceans take up a lot of the heat that we add to the atmosphere. So this is data from since 1960. This is the amount of heat energy in the top 2,000 meters. And this line is the amount of heat energy in the top 700 meters. The reason this line is lower is simply because that's a smaller volume of water. But in any case, the oceans have absorbed around 350 zettajoules of heat energy since 1960. And a zettajoule is 948,000 trillion British thermal units. We're talking massive amounts of heat energy having been stored in the oceans. And thank goodness again. Otherwise, we would see that heat energy remaining in our atmosphere and on the land surface. Okay, why are we concerned about this particular buffering capacity? Well, and again, this is another way of looking at the data on how the oceans have absorbed that heat over time. This is from, again, about 1960 up to 2023. And all those zettajoules have been absorbed into the upper 2,000 meters of the ocean. That is 90% of the greenhouse warming heat from the atmosphere. Here's the scary thing. So year after year, all of these are annual records of sea surface temperatures. And you can see that incrementally, year after year, for many decades, we've seen slight increases in sea surface temperature. In 2023, we suddenly had open space between the warmth that year and the next warmest year. So there was a leap in ocean surface temperatures starting in 2023. 2024 has leaped yet higher than 2023. Why is this happening? We don't fully know. But one possible explanation is that the oceans are starting to reach their limit for taking up heat energy. And that's reflected in the ocean surface temperature. In any case, as the ocean surface gets warmer and warmer, its ability to take on heat from the atmosphere will reduce because it's already got that heat energy in it. It is no longer that much colder than the atmosphere to absorb that excess heat, if that all makes sense. So, the temperature differential affects the rate of transfer of heat from one place to another. And so as the sea surface temperature increases, the oceans will take up less of that heat energy. So what we can expect is that as less of that heat energy is absorbed, we will see a more rapidly rising atmospheric temperature. And that's exactly what that earlier slide showed you. Starting in about 2010, 2014, we saw a rise in the rate of temperature increase. So I believe that rise in the rate of temperature increase probably has more to do with the oceans and reaching the limits on its ability to buffer temperature change, and perhaps also has to do with the terrestrial systems reaching their limits on taking up CO2. So this is from Johan Rockström, who did a TED Talk in 2024. It's well worth seeing. And the way he explains it is that for the last 10,000 plus years, we have been within this 2 degree centigrade corridor. He calls it the corridor of life. And so temperatures have stayed within that 2 degree band. We are now at the upper end of that 2 degree band at 1.2 degrees centigrade warming, and we are rapidly shooting towards 2.7 degrees centigrade warming. So we are leaving that corridor. Within that corridor is where human civilization developed. We developed our current agricultural systems. They are adapted to that range of temperatures and conditions. So we are now leaving that what Professor Rockström describes as the corridor of life. We've seen the effects of this. We see the loss in crop productivity. We see the lower productivity of all natural ecosystems as well. Where it will all end up, we're seeing a whole new different weather patterns with the polar vortex destabilizing and causing Texas to freeze, at odd times of year. Um, so new things are happening. We don't fully know how to predict how this will continue to change, but we do know for sure that we expect more extremes. So what are we doing to climate? We're adding more heat energy to the atmosphere and the oceans. That heat energy is what drives climate, what drives weather, storms, floods, etc. And with that greater energy in the system, we expect more extremes of all kinds. That we know for sure, and we're seeing that in every possible way. So we've seen that there is an increase in the number and intensity of floods, the number and intensity of storms, the intensity and frequency of drought. The only reason this curve is not as high as the others is because how do you measure a drought? Well, a drought occurs in a very large region, and that still only counts as one drought, if that makes sense. Okay, so we're seeing rises in all of these. What should we do? Well, every bit we emit matters. Some people throw up their hands and say, oh, my small emissions don't matter because the United States is producing so much. Well, every bit we emit, it's all additive. It strengthens the amount of heat that we trap, and the less we emit, the less heat we trap. And so in the short or the long term, it's really important for us to do everything we can to reduce that carbon in the atmosphere. So we've got individual carbon footprints that we can work on at a larger scale. We've got collective carbon footprints that we need to work on. These have a much larger effect, but both are very important. We'll talk about how people are working to clean the grid, electric vehicles and heat pumps. Are they really cleaner? And we'll talk a little bit about land use and cement production as well. Okay, so this is from the IPCC report of 2018. And already then we were doing over 40 gigatons of CO2 added to the atmosphere per year. And we projected that if we wanted to stay below 1.5 degrees centigrade warming, we needed to reduce our emissions at a very steep rate. The longer we put off changing our emissions, the steeper the rate will be required. So back in 2018, we were looking, okay, if we don't reach net zero emissions until 2055, then we will have put 3 trillion gigatons of CO2 into the atmosphere. 3 trillion tons of CO2 into the atmosphere. If we stop by 2040, then we could rein it into 1.5 degrees centigrade warming, because it's when we put 2,900 gigatons of CO2 into the atmosphere that we reach 1.5 degrees centigrade warming. These numbers are, even though they're from 2018, they are way out of date. We are now projected to reach 1.5 degrees centigrade sometime in the year 2028, and we've already touched upon it a few times. So again, climate change, temperature rise continues to happen faster than we expected. Okay, and this is just the calculation I gave you. In 2020, we had 2,400 gigatons emitted into the atmosphere. We reached 1.5 at 2,900 gigatons. That meant we had 500 gigatons remaining that we could put into the atmosphere before reaching 1.5 degrees centigrade warming. And in 2020 already, we were putting 59 gigatons per year into the atmosphere. So that was the projection for why we will probably hit 1.5 sometime in 2028. The good news is that at the collective level, countries are doing things or beginning to do things. So France passed a resolution to ban the sale of petrol and diesel cars by 2040. This is a good thing. Is it soon enough? No, but it's much better than nothing. The European Investment Bank announced that it would stop lending to fossil fuel development projects. They announced this in 2019, and they so far have kept their promise. And they're instead investing in renewable energy. So they are also doing a large good thing. The European Union called for net zero by 2050 back in 2018. This is a good thing, as long as they can actually implement it. And some of the countries are doing very well so far. And then in 2019, there was also the ratification of the Green New Deal, which was other agreements between the European nations on ways to reduce their carbon footprints and how much to reduce their carbon footprints. The only standout in that particular deal was Poland. They felt like they were too dependent on coal and could not give it up. Now, fortunately, some countries have actually reduced their carbon footprints significantly, and Great Britain is an example. So they've already, by 2023, they had already cut their carbon emissions in half. So the good news here is that this shows that it's possible. Countries can do this. If Great Britain can do it, so can the United States, so can Germany, so can France. One of our big utilities here in Arizona is APS, Arizona Public Service, and they agreed back in 2020 to the goal of zero carbon emissions by 2050. We have one of the highest amount of insolation, that is incoming sunlight, here in Arizona, and so we should be using solar and wind energy. We've got a fairly large wind resource as well. And so fortunately, these kinds of changes in our electrical generation are moving in the right direction in Arizona. Are they moving fast enough? No. Even if we reached zero carbon by 2050, would that be fast enough? No. But it's a start, and we can push for more. In Flagstaff here, Flagstaff, Northern Arizona, we got the city to pass a climate action and adaptation plan back in 2018. They passed it unanimously on November 20th. In that particular plan, their goal was to be 100% renewable for the city, municipality, not for all the citizens of the city, but for the municipality to be 100% renewable by 2025. So far, the city has reached about 10.4% renewable energy. In the climate emergency that they declared in 2030, again, we were urging them, we being NASCA, the Northern Arizona Climate Change Alliance, and other environmental groups in town. And then we also got them to pass the carbon neutrality plan in 2021. Unfortunately, they did back off from this goal for the municipality, and now they've put all of it. So the municipality and the citizens, the entire city's operations, private and governmental, are to reach net zero by 2030. And now we are battling to keep the city council from modifying that goal and to push them to implement that goal because they're not really always making the right decisions. And this is the case globally. We push for good policies, but then we also need to push for their implementation. This is the case for all the global meeting, the conference of the parties, the COP meetings, oftentimes pass good policies, but then those policies aren't fully implemented. In any case, so it's an ongoing battle, and we have our sleeves rolled up to fight it. We also have a Northern Arizona Climate Change Alliance chapter in Sedona. They have successfully pushed for a Sedona Climate Action Plan. In Flagstaff, we're just primarily pushing for implementation of that plan, and Sedona is now beginning to push for that implementation. Cottonwood, which is a little bit further south, is encouraging their city council to develop a climate action plan, and Prescott is encouraging the Prescott NASCA group is encouraging the city council to pursue a climate risk assessment. And I think they are successfully doing that. And hopefully that's a first step to a climate action plan. In any case, these things need some political will and need some action. We did in this November November election, we elected one of our original NASCA members to the city council. So that's a really important step. We will see, I think that will change the speed of implementation of the carbon neutrality plan. But we shall see. David will be good, but we've got to still lobby the rest of the city council. Okay, so the city comes up with all these plans. One of these overpass over Lone Tree is cement. We are trying to urge them to use low carbon cement, or better yet, carbon absorbing cement substitutes. And we'll talk about that in a moment. So anyway, those efforts are ongoing. Other more individual efforts are smaller groups of people suing government to protect their rights. In this case, a judge sided with the teenagers and college students who were pushing to get the state of Montana to enforce the constitutional right to a clean and healthy environment. That was stated in the Constitution. So several of the laws they had passed back then to promote fossil fuel development went against their Constitution, and this judge ruled in their favor. So these kinds of battles make a difference. Here in Northern Arizona, we've got various climate action teams under the Northern Arizona Climate Change Alliance, the Pet and Pedal Cat, the Net Zero Cat, Climate Educators Cat, Fossil Free Arizona Cat, Green Burial Cat, and so forth. We now have a radio show called the Spotlight on Climate Radio Show, and a monthly column in the paper, Spotlight on Climate. You can see those things on the NASCA website if you're curious to see what the content on them is. We've done shoe strikes in front of City Hall back in the days of COVID when we didn't want to gather in large numbers. So we get active in every way we know how. And I encourage you, if you're not already doing these things in your communities, please do them. The sooner the better. Find strong allies. Get things done as much as you can. So global solar power. This is something that has been moving in the right direction. Again, not fast enough, but right now the world has over 2,000 gigawatts, that is 2 terawatts of solar power capacity. This is a good thing. Here's how that's changed over the years, and here how the different regions of the Earth countries have contributed, some more than others. But in any case, solar is increasing, and its price per kilowatt hour generated has been plummeting as the volume of photovoltaic panels and battery storage and these other things has increased. Global wind power all over the world has a capacity of 1,100 gigawatts or 1.1 terawatts, including here just outside of Flagstaff. This is our mountain. Flagstaff is right at the base of this mountain, and this is out of the Perrin Ranch. NAU designed these wind turbines, students in the engineering program at NAU, and helped to install them. And so we've been involved in various ways. So this is the trajectory for the inclusion of wind power up through 2023. Most of it is onshore, but there's also a fair amount of offshore wind power now being placed, particularly off the coast of places like Denmark. So these are all good things. And accordingly, as the volume of that production, that generation has increased, the price has come down. And since at least 2017, the price of onshore wind per kilowatt hour has been $42 for fixed axis photovoltaic, $44 per kilowatt. For tracking photovoltaic, $48 per kilowatt. and offshore wind is a little bit higher, but still all of them are less expensive than coal, than gas, than coal or gas with carbon capture and sequestration, and much less expensive than nuclear. Nuclear is by far the most expensive way to generate electricity. Even though it does have a slightly lower carbon footprint, it's very expensive and has all kinds of other environmental footprints. Okay, this is generating volume. So how much of the world's electricity is generated by coal or by wind? And if you look at that, the amount of coal used to generate electricity has been declining, and the amount of wind to generate electricity has been increasing, and the amount of electricity on the global grid generated by wind surpassed that generated by coal earlier in 2024. So this is good news. We're heading in the right direction. Is it fast enough? No. And this is again the amount of electrical generation from all these different sources. Natural gas is still higher than renewables, unfortunately, even though it is more expensive. You'd think that in a capitalist world, we would be implementing these renewables more quickly, but we are implementing them. So wind, hydro, and solar are coming up. Biomass and geothermal are staying pretty steady at a low level. Okay, so the Chevelon Butte wind power plant is just being installed to the south and east of Flagstaff at Chevelon Butte. Here are various wind and solar installations that we have all around Flagstaff. This one was put in 2009, 2012, 2022, 2023. And the Babbitt Ranch solar power plant is starting to be built now. Overall, we have a total of 1,424 megawatts of clean electricity available. So the time for us to go electric is now, because if you shift from a fossil fuel furnace to a heat pump, that's only as clean as how clean your electrical source is. And the good thing is we've got nearby production of clean energy. Some people express the concern that all that solar is going to take up a massive amount of land. And really, if you take a look at the numbers, it will require much less than 1% of the land surface to completely power the entire world's electricity need. So that argument is just a baseless piece of propaganda. For wind, the total is less than 5% of the land surface area. And that's, that's not counting the offshore wind. And here are all the details of these things. We won't get into those, but in any case, the claim that renewable energy is going to take up all of this land is hyperbole at best. So, and the good thing is, as we get more and more clean electricity, electric cars are cool. And it all depends. How clean they are, all depends on the source of the electricity. So we really need to push for utilities to stop burning fossil fuels at all. I'm looking forward to this particular electric vehicle. It's now on lots. They've been promising it since 2020, but it's now available. And as soon as my model comes in, I will be purchasing it. So I'm really looking forward to that. Okay, of course, electric vehicles are not the best solution either. Walking, biking, and non-fuel cars are even cooler than electric cars. So if you can get around by these means, that's the best. If you have to carry a load or go a longer distance, then electrical vehicles are the next best, and fossil fuel vehicles should be outlawed. Here's another kind of cool non-fuel vehicle. I love these pictures. I would love to have an engine like that. And of course, there are also man-powered vehicles. This is basically a converted bicycle that was entered by some NAU students in uh, a non-fuel car race, and they won some awards. We do have a lot of electric and hydrogen cars being produced in Arizona. So Phoenix Motor Cars has been producing electric trucks since 2019. Lucid Motors in Casa Grande, Arizona since 2020. And the Lucid Air, which they produce, has a 500-mile range. So for those folks who have range anxiety relative to electric vehicles, that would be the one for you. Nikola Motors is producing hydrogen trucks. And this is really important because electric freight trucks, to take a long trip, they would have to carry so much weight in batteries that they would have no weight remaining for payload. So having hydrogen as a power source for driving those freight trucks is a really important way to do that because the hydrogen is much lighter. They also produce a pickup truck that's a combination of electric and hydrogen, and it has a 600-mile range between those two sources of energy. Anyway, so there are great innovations, and we just need people to jump in. R is the footprint. So let's say you buy an electric vehicle. One of the complaints that people have is, well, shoot, that takes a bunch of carbon to produce that vehicle, and lithium and other things, but carbon. So what is the actual footprint? Well, initially there's a slightly higher footprint for an electric vehicle than for producing a new combustion vehicle. But before the year is over, they are the same in terms of carbon footprint because of all the fossil fuel that combustion vehicle is using to power itself. And then over its lifespan, the footprint of that combustion vehicle is much greater than that for the electric vehicle. So yes, we do need to go electric, and yes, we need to push for clean sources of electricity. So prices have been coming down. One of the concerns about electric vehicles is price. And for Tesla and all electric vehicles, the price has come down and sort of merged toward the price for combustion vehicles, which have also been coming up. So that's good news. They're still a little bit too expensive, but nonetheless, the price has come down to make them more equivalent to their combustion vehicle equivalents. As volume increases, the price of lithium batteries has dropped tremendously. And it may be leveling out now, but in any case, that's dropped, and that has contributed to the price drop in electric vehicles. The better news is actually this. For the United States, battery electric vehicles and internal combustion vehicles have been changing in volume of sales. So 2023 relative to 2022, there was a 47% increase in electric vehicle sales and only a 10% increase in combustion vehicle sales. 2023 relative to 2021, EVs had increased tremendously while the sales of combustion vehicles actually had declined. And since 2019, combustion vehicle sales have declined by 14%, while electric vehicle sales have increased by 385%. So these are all very good trends. One of the concerns about electric vehicles is lithium and other minerals required. And this is just an overview of the reserves we have for lithium, copper, cobalt, graphite, neodymium, and nickel, which are all needed in various forms for going electric. And you can see that we do have enough lithium reserves, and the potential resources, those are undeveloped reserves of lithium that we know of. So we will not run out of these minerals that we need to make this transition. And over time, those potential resources, that is, those current reserves, the potential resources become current reserves. And so those will only increase over time. So that's good news, but still, there are issues with mining lithium. And so there are human rights issues and there are pollution issues, and those need to be cleaned up for sure. No question about it. But when somebody tells you that we can't go electric because of the mining footprint, it's important to remind them that all of the mining required to transition to clean energy is about 300 million tons of material. The mining per year for fossil fuels, so by 2050, I'm sorry, the mining by 2050 for fossil fuels dwarfs any such mining impact. So for fossil fuels alone, 15 billion tons. So it's important to remind folks who are concerned about the mining impact of the transition that the current mining impact of fossil fuels will dwarf any such impact for the transition. All right. Heat pumps are another good way to get away from gas burning furnaces. And good news here is that heat pump sales have actually reached the level of, of gas furnace sales and surpassed it. So heat pumps are being installed all over the United States as well as globally. So primarily Europe added to the United States. We've seen tremendous increase in the number of heat pump units. And there are various kinds of heat pumps and so forth that we won't get into. I'm looking to install hydronic heat pumps in my house in the very near future. And that's where you use a lot less refrigerant in these heat pumps. One concern is that there is refrigerant, which are CFCs, and those destroy ozone. So hydronic, instead of transferring the heat into a refrigerant, they transfer the heating or the cooling into water, and then water transfers that heating and cooling to an air handler. So there's still some CFC refrigerant in the core of these hydronic heat pumps, but it's much less because they use water to transfer the heat energy. All right, so I mentioned earlier that soils contain a huge volume of carbon, all of that dead material, the roots, all that stuff. And it's over 2,305 billion tons of carbon in the top 2 meters of the world's soils. And when we till soil, we speed up the release of that carbon into the atmosphere. So regenerative agriculture, which puts more carbon back into the soil, permaculture, which doesn't till, it just replants without tilling the soil, and reduced tillage are all ways to keep more carbon in the soil, and people are doing that. So regenerative agriculture, which is putting more of the biological material back into the soil, can store 1 to 10 metric tons of carbon per hectare per year, depending on exactly the details of how it's done. But when I go home to visit relatives in Bavaria, that soil is black and rich, and it's because they have these kinds of horizontal bins or bunkers or silos, whatever you want to call them, and they ferment the wastes from last year's crop. And then they take that fermented material and manure and other biological materials and spread it on their fields. That keeps they have to use less fertilizer, less pesticide, and so forth. And it keeps more of that carbon in the soil. So we need to go back to these older regenerative types of agriculture, which stop just depleting carbon from the soils and actually put more back in. Cement production releases a fair amount of CO2. This is much smaller footprint than fossil fuels, but it's significant. It's like the third or fourth highest source of CO2 from human emissions. But there are now cement substitutes. So for instance, Biomason is a company in the eastern United States. They produce bacterially grown cement. And they can make cinder blocks with this. And it actually gets all of its carbon material out of the atmosphere. So it takes CO2 out of the atmosphere to build that cement. And here's what those blocks look like. They are now working on turning this product into a pourable fluid cement that can fill molds and so forth. So these are good things for us to be doing, not only in general terms of putting out less CO2, but also really absorbing some CO2 from the atmosphere. So we're all in this together. John Kerry referred to this as World War Zero. If we consider it that way, we need to go all out, resource-wise, effort-wise, in every way to reduce our carbon footprints to zero. I don't know if World War Zero is necessarily the best name for this effort, but in any case, it needs to be at a very high scale. And again, if you're not part of such a climate action team or an organization that puts these together, think about forming one and joining a climate action team. You can form an overall organization with many teams, or just form a single climate action team, whatever you can handle, whatever problems you can see that you might be able to solve in your area. Because we want to avoid this. This is the temperature change that we have seen from 1850 up till now and up to the year 2100. Each turn around the circle is a year. You can see the months around the outside, and you can see two things. Temperature is increasing, but also the rate of increase is increasing. So this is a good way to share with people what is going on. It's a good visual to sort of grasp the enormity of the problem. All right, so with that, I will open it up for questions. I want to urge you all to be climate ambassadors. Everybody you know should be part of this effort. And if they're not, then please take all the information I just gave you as a resource to help convince everyone you know to join in the fight. If you have any questions for me about any of this, you can always reach me at my email address. It's just my name, stefan.sommer@nau.edu. Even though I'm retired, they still let me keep my email address. And thank you all very much.
Yeah. Thank you, Stefan. That was really, really interesting, and thank you for presenting all the latest data and developments in such a clear way. We have quite a few different questions
Very
that
good.
have come into the chat. I don't know if you can also see the chat so you can read along.
I can see them, but if you, point out whichever
So
ones
the
to
first
me.
one is it true that APS and SRP rate structures discourage residential rooftop solar?
It is true, and it's unfortunate, and we need to fight that at the Arizona Corporation Commission, which makes those rules for our utilities. Um, One interesting note, though, is that SRP did that to its customers, and they also charged the customers who had home solar a higher rate for the delivery of their electricity to them. And so they were taken to court for that, and they lost. So that kind of business practice, they've gotten a slap on the wrist, and they are no longer doing that part. But we still need to work with the Arizona Corporation Commission to get them to give home producers a good rate of return on the electricity that they produce. Now, it's true that electricity that's produced by home producers still needs to go through the grid, and the utilities maintain that grid. So they do deserve to have some small amount for that service, for delivering the electricity. But the current rates are way beyond that cost. And so they should be much better in terms of supporting the home producers.
Mm.
I don't know if that answers your question, but that's what pops into mind at first.
Then we have two comments, but maybe you can also comment on them. So
Okay.
we, Liz writes that we also need to rethink the way we commute. Shared car platforms are encouraged in some cities in Europe, and this has great results in terms of low emissions. Not every family has to get a car now. And then also Ed says there's a new sodium battery tech that's supposed to replace lithium in several applications too. Um, whether you do you have any responses to these?
I don't know much about the sodium batteries. I've heard of it. That would be good in terms of reducing the lithium impact. We should be recycling all of our batteries.
Mm.
That's a really important source of lithium as well. So, there are various things we can do, including finding new battery technologies. Um, and I think one of the things we need to think about is that when we have a wind power plant or a solar power plant that is producing greater amount of electricity than the demand of that moment, that amount of energy needs to be stored. One way is batteries. They generally have a higher chemical footprint of one sort or another. But another way is to use that excess electricity to hydrolyze water and turn it into hydrogen. And hydrogen can be stored, hydrogen can be transported, and we need a hydrogen infrastructure if we're going to have things like freight trucks.
Mm.
Hydrogen isn't the best fuel necessarily for everything, but for certain applications, it would be very important. So thank you for that question, Ed. I'm not sure if my answer answered everything you were thinking
Mm.
about, but ask again if I didn't.
We also have another question from Bob Sommer. He's asking how to talk to climate doubters or deniers or the hopeless.
That's a really important
Mm.
question, and it's one I've grappled with a good bit myself. I'm trained as a scientist, so I tend to make data-driven types of presentations. Those aren't necessarily the best for communicating to a climate denier because they've got their own facts that they get primarily from the propaganda campaigns put out by the fossil fuel industry. They spend hundreds of millions of dollars a year putting doubt and misinformation into people's minds. So it's hard to overcome that with facts. So emotions might be better. When you're just talking to somebody one-on-one, the best thing to do is to start with a question. What do you think about climate change? Based on their answer, if they start talking about economy or pollution or health or whatever, you can give them an answer about carbon footprint in relation to their primary concerns. You want to find a way to get into their thinking, into their what's already in their brains.
Mm.
Um, there's various ways to do that, but asking a question at the beginning can really help to connect to what
Mm.
they're thinking and address their specific things rather than just going off and saying, yeah, climate change bad and climate change this and that. You choose something that they're interested in.
Yep, thank you. Um, we have two more questions, one in the chat and one raised hand, and we'll get to both of these. Um, so first, Tom Dresler is asking, do you think a high-speed rail between Tucson and Flagstaff would have been a better investment than the millions spent on increasing lanes, which enable further automobile traffic and more combustion cars?
Yes, perhaps. I don't know all
Yeah.
the details of the carbon footprint. So certainly putting in the high-speed train would have a carbon footprint. If it was electric or hydrogen, then over time it would have a lesser footprint than all of the combustion traffic.
Mm.
So yes, I think those kinds of transportation solutions are good, but in every case, you need to calculate what's the relative carbon footprint. I believe that a high-speed rail probably would, from the get-go, be a positive thing for overall carbon footprint. but you would also need to convince people to use it and not use their vehicles. That's often the problem with public transportation. We are so acculturated into our private vehicles that it's hard for us to think outside that box. You know, in places like Germany, when I was a kid and would visit relatives in Germany, there were buses and trolleys and things that everybody and trains, trams that everybody used. And we would go from Echtelingen to Stuttgart on the trolley for our shopping or whatever.
Mm.
Now they've been taking out those bus lines for a few years and suddenly realizing, oh, shoot, we shouldn't have done that. But anyway, so people are more into their individual vehicles there now as well. But we need to shift that back in the other direction, and high-speed rail would be one way to do that. Fortunately for us here in Flagstaff, we have Mountain Line bus system, and they are further ahead than all the rest of the city in terms of converting to electric. They already have several hybrid buses and now a couple of fully electric buses. They're building a new bus terminal that is oriented towards repairing electric buses and charging electric buses and all of that. So they are converting to be fully electric as soon as possible. And then, the budgetary constraints are the only thing that's holding them back. They have a desire to go all the way. So there are lots of different levels of issues with public transportation, but generally speaking, it has a lower footprint. We should go there as quickly as we can. So Joyce, go ahead.
Thank you, Stefan. Excuse me, I've watched one of your presentations before, so my first question has to do with that. And then if you would allow me to, I have a little bit of a informational speech after. So I did, like I said, I attended one of your meetings, and at that meeting, you talked about taking an EV battery when it's used up its life, excuse me, in an EV and using it for household purposes. Since then, I've had numerous questions of, we need more information on that. How does that work? First of all, I'm from Minnesota and I do own an EV. I have range anxiety because when the temperature in Minnesota drops, my range drops drastically. But anyway,
Right.
so if you could answer that first question, and then after I do have some comments. Thank you.
Well, thank you very much, Joyce. Those are good points. And I think if I remember that presentation right, I was talking about using your existing electric vehicle as a storage. So while your photovoltaic system is operating, you can store that electricity rather than having an additional battery system using your car battery. And you need the right inverter system and so forth. And I don't know the details because I haven't done that sort of thing. But your local electrician will know what it takes, and probably the person you bought the EV from will be able to tell you if your particular EV has that ability.
Yeah, so I may have misunderstood. The second
But
point
but
would
but but
be,
your idea of using it, once the vehicle needs a new battery, maybe I don't know much about the life of batteries and to what extent that would work, but that's a good idea too.
and I forgot, this is a wonderful presentation. In my opinion, it's for the people that are just getting started in the environmental climate change issues. I'm just wondering if you are all aware of the Yale project on climate or program on climate. It's just for people that are attending this that want to deep dive into climate change and what they can do, small steps, big steps to reduce their carbon footprint. I personally belong to an organization called Citizens Climate Lobby. Don't know if you've ever heard of it. Um,
Mhm.
they have wonderful information in their websites. In Minnesota, we have something called the Land Stewardship Program. So my point is that I feel like a very small fish in a large sea of people that want to do things for the environment and feel lost. Like, okay, I can swim today and catch an air bubble, but then something happens like politically in our government, and you're like, oh, okay, back to square one, maybe 2 steps forward, 1 step back. But anyway, I'll stop there. Thank you.
Well, thank you for mentioning those programs. Yeah, CCL, we've got a branch of CCL here in Flagstaff as well. And they put on wonderful conferences. And their main focus is federal lobbying. But that's a really important thing too. So we try to work with them wherever we can. And about this presentation, so, how much can you cover all of the different possible solutions and the details of them in an hour and 15-minute presentation? You can't really cover much, but I hope I gave everybody sort of at least a connection to some of the ways that people are doing things. NAU also has a graduate program in climate change. Climate Science and Solutions is the name of the program. So they have an in-depth program for that. And occasionally they have online classes, but in any case, yeah, it's good to take advantage of those kinds of offerings.
I think that was all the questions. Wait, let me just, oh yeah, everybody's just saying thank you. There were some questions about whether the recording will be available, and it should be available in a week's time on nasca.org. So if you could look out for that. And somebody's also asked if you could share, Joyce, the link of the program you mentioned, and also Stefan, if you could share the link of the programs that you mentioned in the chat.
Okay.
Yeah.
I'm not sure if I got the link ready at hand for
Okay.
the Climate Science and Solutions program, but it's the I'll type this in.
One more quick question. I didn't catch your website, so if you could put that in the chat as well, your email address or whatever it was you told that we could reach you. Thank you.
Very good. So there's the NASCA website. If you go to NASCA website and there's a drop-down list at the top under our work, you will see a link to Climate Talks for Everyone. And that's where the upcoming talks are advertised and the archived talks are available to view. And my email address again. So yeah, feel free to contact me with any questions. You'll see a lot of the NASCA organization by looking at the NASCA website. But of course, there are always more details to organizing and so forth. And we do have a couple of community organizers who work for NASCA, one in Flagstaff and Sedona, and one down in Cottonwood and the Prescott area. And so, they know more about that community organizing than I do. So if you're interested, I would connect you with them.
Great. If there are no
So
more,
thank you all very much for
yeah,
coming.
thank you very much to everyone. Yeah, if there's no more questions, I think we'll end
Go
it.
out, go forth and be ambassadors. Right. Thank you all.
Cool.
Thank you both. Thank you, Stefan. That was very excellent. Thank you, Frida, for being on too.
Thank you very much, Frida. And thanks, Rolf, for setting it all up.
Yeah.
Thank you.
Okay.
All right.
Have a good evening. Yeah.
Good to
Bye.
see you all.
Or good morning.
Good morning to you in Sweden. Yes.
Yeah. Bye.